All right, it's close enough to 8. For those of you that are on Zoom, please type something into the chat to let me know that you're here. The roll sheet is out and about for those that are physically present. So I apologize for having to cancel class on short notice on Wednesday. Students feeling not great, a lot of vomiting, all that kind of good stuff. Did not want to work, so I didn't. I asked you to review, I believe, 2 sections. The first was on Pmos transistors, and the second was on transistor biasing network. How many of you actually bothered to do this? See, nobody raising their hand. Seems about right. All right, so we're going to spend a few minutes going over Pmos transistors, and then move along to the biasing networks. So before we jump in fully to Pmos transistors, though, I want to revisit a couple of quick topics about an Nmos transistor because it's going to inform things. So let's consider a simple Nmos transistor. Let me make it a little longer, actually, just in case we need it that way. And here's my polysilicon gate. All right, so let's say first off that my source and my body are tied to ground. And VGS will be greater than VTHN, meaning our transistor is on. And we don't exactly know what's going on with VDS just yet. Well, actually, let me change my statement. Let's say that VD is also grounded. So to be clear here, this is my body terminal, this is my source terminal, this guy's my gate, and this guy's my drain. So under this condition, what has happened internal to the device? So it's definitely not going to be in the saturation region because VDS is 0, which is less than VGS minus VTH, because I'm saying explicitly that VGS is greater than VTH. So it's not in the saturation region. So what is the role of the gate voltage? What does the gate voltage do in an Nmos transistor? The whole purpose of the gate voltage is to either cause or not cause the inversion condition, which establishes the channel full of free charge carriers, right? So in a situation like this, where our source and our drain are both at ground, but VGS is greater than VTH, we have strong inversion. So we have all of our free electrons hanging out around here. But do we have any current flowing through the device? This is a fantastic test question. I think I've been asked it and have subsequently asked it to students every time I've encountered this material. Pozniak is shaking his head, no, but looking questioningly.
I don't know why it just
right. You've got it. So these are field effect transistors, okay? What drives, so the gate voltage establishes kind of a collection of free charge. But you need a potential difference between the source and the drain to cause current to flow in one way or the other. So if VD is now greater than 0, we have an electric field oriented from the drain, because it's at a higher potential, to the source because it is at a lower potential, and that is causing electrons to flow in which direction? So the electrons are going to move from the source to the drain. So this is the direction of electron flow, and thus the direction of current, positive current, is from the drain to the source. So for our schematic diagram representation, that is why let me see how I want to draw this real quick. We have this indicated direction of current flow, assuming the voltage VDS and the voltage VDS are positive. This is technically true even if VGS isn't greater than VTH, because we have something called sub-threshold current that's beyond the scope of this class. And I guess I should technically draw the arrow there to indicate which one is my source. And just to cover all the bases, gate, drain, and source terminals, where I'm assuming that my body is tied directly to my source, okay? So this is how an Nmos transistor operates. The gate, or the presence of a positive voltage at the gate, is what's causing inversion. Once that gate voltage exceeds the threshold voltage, then we have strong inversion, meaning that our channel is well established, it's full of free charge carriers, and a potential difference between the drain and the source can drive the current in one direction or the other. The drain technically is the terminal at a higher potential than the source, which is always at a lower potential in an Nmos transistor. It does not remotely matter which one I put at high potential and which one I put at low potential, because it's a 4-terminal device and I can always just tie my source, or excuse me, tie my body to the one at low potential. The source and the drain are identically doped. They are identical in size. This is a completely and utterly symmetrical device, not like a BJT at all. So for the Nmos transistor, the drain is always at a higher potential than the source, which is why the current flows from the drain to the source, all right? In a Pmos transistor, we have something very, very similar, and it confuses the bejesus out of me as to why the textbook throws all these weird, crazy negative signs and all that kind of stuff in, because it doesn't make a lot of sense to me. Yes. Body. Yep, that's the body connection, which is ignored a lot in this textbook, which I also don't much care for. All right, so that's what's going on in an Nmos transistor. So let's take a look at a Pmos transistor. And this is where the book and I have a pretty strong disagreement. I'm going to not put it in a well and say that I have an N-type substrate, so just so that I can get away from drawing some unnecessary things that don't really add to the discussion. Here's my gate. Here's my source. Here's my drain. Here's my body. Okay. So if we were wanting to avoid body effects, we would tie our source to our body, just like we did previously. So we're going to do that because body effects are just going to make everything more difficult to understand. All right. So we need to think about how this guy is expected to work based on how our Nmos transistor works, right? So we have an N-type substrate, which means we have an excess of holes all throughout it, right? For our Nmos transistor, we had a P-type substrate, excuse me, so we have, sorry, an N substrate for our Pmos transistor, meaning we have an excess of electrons that we need to drive away from the channel, okay? So how are we going to accomplish that? There's really two ways to do it. One is the way the textbook describes it, and it's the way that I don't really care for. Negative voltage on the gate will absolutely do it. Here's why I don't like that, okay? Typically speaking, you would see on a Pmos transistor that the source is at the highest potential in the circuit, unless there's a resistor or something like that in the way. So I'm going to call this guy, I'm going to tie both of those guys to VDD. So in order to establish the inversion condition, then the gate voltage just needs to be less than the source voltage by the threshold voltage, okay? So it's operating the exact same way, except that we see that VSG needs to be greater than VTHP to cause inversion, okay? VSG greater than VTHP, excuse me, or strong inversion. The reason why I prefer to talk about it in this way is because it's going to turn out that all of our voltages will be positive. So we're not going to have to worry about having lots of extra negative signs here, there, and everywhere that are going to cause us dumb errors and make us wind up changing the direction of our current, which is what the book does, which again is stupid in my opinion, okay? So strong inversion will occur when the gate voltage is sufficiently less than the source voltage. And I'm writing that as VSG, where the source is implicitly at a higher potential than the gate. When it's greater than the threshold voltage, we get strong inversion. All right. So right now my drain is a floating potential, right? If I tied this guy to VDD, the power supply as well, what I should see is that I have a whole bunch of holes here. Because I've driven out all of the electrons and I've attracted holes into the channel area. And so I have a solid conducting path between the P plus region of the source and the P plus region of the drain that is connected by that excess of holes within the channel. So now I need to figure out what I need to do to cause current to flow in this guy. What did I do to have current flow in the Nmos transistor? A potential difference, and that's all I need here, right? So let's say that instead of being at VDD, my drain is now at some voltage VD less than VDD, or actually it would be better to be less than VS. I have a potential difference, right? What is the direction of my electric field here? Field is directed to the right. What is the direction of my whole flow? To the right. And what is the direction of my current? Well, I just drew it. It's also to the right. So we see again, or we see here that our current is flowing from our source to our drain. In the book, for whatever reason, in its illustration, it shows that the drain current is flowing from the drain to the source and then introduces negative signs in key places in order to make that true. That to me is very, very confusing, okay? So instead, we can see that the Pmos transistor behaves exactly like the Nmos transistor, except we just have to switch the subscripts on our voltages and everything works out exactly, okay? So from this, we can say that our drain current, let me draw a picture here to kind of explain what our point of reference is. So for our Nmos transistor up here, everything is based around the lowest possible potential in the circuit, which is ground. And for our Pmos transistor, this simple biasing consideration where we're deriving everything is based on the highest point and the highest potential point in the circuit, our power supply voltage, VDD. So from this, we get the relationship ID is equal to mu P Cox W over L VSG minus VTHP times VSD minus 1/2 VSD squared. This is our triode region operation. So VSD needs to be less than VSG minus VTHP. And then we have ID is equal to 1/2 mu P Cox W over L VSG minus VTHP quantity squared 1 plus lambda VSD for VSD greater than VSG minus VTHP. Those are our Pmos equations. We can get those directly from the Nmos equations by simply turning the subscript around. So everywhere we saw VGS, we now have VGSB. Everywhere we saw VDS, we now have VSD. Everywhere we had VTHN, we now have VTHP, and that's it. That's all the consideration that we need. It takes care of everything. It doesn't have currents flowing in weird directions that are counterintuitive. It doesn't have extra negative signs and all that kind of jibber jabber to screw things up. All the voltages here are positive, including VTHP. To me, this is a much, much easier way to look at a Pmos transistor and actually understand what the heck is actually happening here. And these two models that we've brought in here actually can illustrate something pretty interesting as well. Before we get into our biasing circuit, this is technically the subsection after the biasing circuits. Do I need to clarify something? I see some people looking at the board with confused faces. Mr. Washington, what's up? Yeah, first is triode, second is saturation. write that down just so we're clear. And
Dr. Harmon,
yes,
what is the main difference between the initial condition we were given versus the inversion condition to like look out for?
so in our initial condition, I'm not entirely sure that I understand your question. So let me say this. In a Pmos transistor, inversion occurs when the gate voltage is sufficiently below the source voltage. And that strong conversion condition is given right here. When VSG is greater than VTHP, where the gate voltage here is on the negative polarity terminal, so that means it's less than the source voltage, we get strong inversion. So that's how we turn the transistor on as a digital switch, right? Then establishing some potential difference between the source and the drain is what actually causes current to flow through the device. And the current flows from the point of high potential, which is the drain, to the, which is the source, to the point of low potential. So just to be clear, this is my source, this is my drain, this is my gate, this is the direction of current flow. Did that clarify things at all?
Yes, thank you.
Yep. All right. So we're going to skip over biasing circuits just real quick, just to point something out here, okay? So let's say that I have the following circuit. All right, so I have an Nmos transistor with my source grounded. So let me GSD. And I have right now an open circuit as a load, but that's just representing how I would connect this to something else. What does this circuit do? I'm gonna put a dashed line here. At 5 volts or whatever, some load resistance. What does this guy do to that particular load resistor? Our transistor is on. There should be some potential difference between the drain and the source, assuming our resistor is correctly sized here. I guess what I'm trying to get at is if we tie our source to ground and we apply a gate voltage large enough that we know it's on, this guy is acting like a simple current source, okay? This is how we create current sources, right? Now, this goes way back to circuits 1 and a lot of hand wavy stuff that I and all the other professors did then, because we talk about voltage sources a whole heck of a lot because they're easy to understand. They're batteries and things like that. But we never have a real clear example of what a current source is from a practical standpoint. And it's because they're all based on transistor circuits, which you don't have enough knowledge to deal with way back in circuits 1, 2, and even 3, okay? That's where all this stuff is coming from. All those current sources, whether they be a DC current source or dependent current source, are all just simple transistor circuits. So this is how you make an Nmos transistor act like a current source. For a Pmos transistor, you tie the source to VDD, and let's see, here's VG less than VTHP. Here's the drain. This is how you make an Nmos transistor behave like a current source, or excuse me, a Pmos transistor behave like a current source. We're going to use current sources in 336, so these MOSFET-based current sources, to load differential amplifier circuits and all that kind of stuff when we get to 336. So this is just a very quick introduction of how these can be used very, very basically as a current source when we need them. All right. Let's move along to our biasing circuitry. All right. So there's only 2 that we need to pay attention to this time instead of, I think it was 4 or 5 last time. Okay. We have our 4 resistor bias circuit. Which we'll talk about literally right now. And then towards the end of the class, we'll talk about a self-bias circuit, and that's all we have. So our 4 resistor bias circuit looks something like this. And some of these resistances might be 0. I guess technically one of them can be an open circuit as well. So we have some resistance RD between the drain and the power supply voltage. We have some resistance RS between the source and the ground, gate, drain, source. And this is going to be resistor R1. Let's put another guy down here as a resistor R2. Okay. So this is our 4 resistor bias circuit. Okay. We're going to first look at the large signal model, because this is a DC circuit, and gain some insights on why, in some ways, MOSFET circuits are a little bit easier to analyze than BJTs, and in other ways, they're a little bit more complicated. All right, so our large signal model. I think I can draw it over here on the side. Okay. So I'm going to start. Here's my gate. Here's my source. Here is my drain, all right? So between the source and ground, I have that resistor RS. So I'm just gonna go away, calendar. Sneak that resistor in right here. This voltage will be VGS, whatever it happens to be. The currents being flowing between my drain and my source is my drain current, whatever it happens to be, and we're going to talk about that momentarily. between the drain and the power supply, I have that resistance RD. Between the gate and the power supply, I have a resistance R1. And between the gate and drain, excuse me, gate and ground, sorry, I apologize for misspeaking. I have that resistance R2. All right. So a couple of things that we can notice here. There's one that's a real big one, okay? Because there is an open circuit between the gate and the source, no current can split off on the left-hand side, right? So we know exactly what VG is, the voltage applied at the gate, just using simple voltage division, okay? So that's our first observation. VG will always be VDD times R2 over R1 plus R2. Can't be anything else, all right? In reality, we might actually see a small amount of current flowing into the gate of a MOSFET transistor. But that amount of current would be on the order of picoamps to femtoamps, meaning it's crazy tiny. So it's at least 6 orders of magnitude smaller than what we will see for drain currents, okay? So it's not hurting anything whatsoever to treat that between the gate and the source as an open circuit. Doesn't harm us in any way. All right, so we know what our voltage is at our gate. Another thing that hopefully is pretty obvious is that the drain current flows through our resistor RD, and it also flows through our resistor RS. So we no longer have any 1 + 1 over beta or any of that jibber jabber to worry about. The same current flows through all the resistors on the right-hand side of the circuit. So from this, I can see that VS is simply RS times ID, and I can see that VD is equal to VDD minus ID RD. So to get either of those voltages, we're going to have to know what the drain current is, all right? From these relationships, we can actually write all the other different things we have, right? Because we know that VGS is simply VG minus VS, VDS is VD minus VS, and things like that. So these simple observations let us jump right into developing our kind of fundamental equation for this guy. So without channel length modulation, we are going to have VGS is equal to VG VDD times R2 over R1 plus R2 minus VS, which is RS times ID. And so I'm going to go ahead and substitute in an equation here. So the first thing that we are going to do, or we're going to make a large assumption, all right? We are going to assume that anytime we have this full resistor biasing circuit, we're going to assume that the transistor is operating in the saturation region. We're going to have to come back and verify that. The reason that we always assume that it's operating in saturation region, you will shortly see, is because the math is easier, all right? If we assumed a triode operation, we would have 2 quadratic equations that are coupled to each other that we would have to solve for, which takes forever to do iteratively. It's really quick to do in MathCAD, as you'll see. So it's a definitely use your computer kind of situation. So assuming saturation operation, I'm going to put in my saturation drain current 1/2 mu n Cox W over L VGS minus VTH quantity squared times my resistor RS. And just to make the math a little bit less complicated on me, I am going to call this quantity 1/2 mu n Cox times W over L, an arbitrary constant K, because I don't want to have to keep rewriting it over and over and over again. Okay. So. This is going to I don't want to say simplify, but using algebra, we can make it look like this. And from this, we can rearrange and we will find that we are going to have K times RS times VGS squared plus 1 minus twice K times RS times VTH times VGS plus K times RS times VTH squared minus VDD times R2 over R1 plus R2 is equal to 0. I wrote it this way for a very specific reason. All right. Let me just make sure that I've got, so K RS VTH squared. Yep. 2K RS VTH. Yep. Okay. So the reason why I wrote it this way is because in the previous form up here, it may not be immediately identifiable that there is a quadratic relationship in this circuit, okay? So we have a simple quadratic equation with one variable, VGS, and it's going to give us two solutions because it's a second order polynomial, right? So using our good old quadratic equation, we could find that K times RS is our quantity A, this whole guy right here, 1 minus 2K RS VTH is B, and then this whole guy right here is C. And so from this, VGS will be negative B plus or minus the square root of B squared minus 4AC all over 2A, right? Two different solutions, only one of which I think how to put this correctly. Only one of these solutions is going to be positive, or at least in my experience, only one of them is going to be positive. It's going to be fairly easy to tell what to do. So with that in mind, I would like us to work a numerical example real quick, okay? So let's say that we have the following circuit. lambda equal to 0 because we're not quite ready to throw channel length modulation into the mix here. So these are our parameters. So what I would like you guys to do is take a moment and tell me what A, B, and C are. Right? Think you have enough information. Remember, K is 1/2 mu n C ox times W over L. If you haven't seen this in your textbook yet, anytime there is a fraction written beside a transistor, that is telling you what the width to length ratio of that transistor is. Okay. I will say that if you use LT Spice to do any simulations or anything like that to help you out, when you specify it for an Nmos or a Pmos transistor in LT Spice, it is looking for a physical unit of length for the width and the length of the transistor. And if you make it too large, like I was doing an example in 438 last quarter, where I wasn't paying attention and I had it as a 10/2, forgetting that it was going to take that as it was 10 meters long in width by 2 meters long in channel length, that kind of screwed with my currents and things like that when I was trying to put it into a circuit. So. RS was 0.5, 500 ohms. Where did I? Oh, yeah, 0.5, sorry. Anybody got a numerical answer for A, B, or C at this point? That is not what I got. 1/2 mu n C ox. W over L is 5. So that I'm going to store as. So 5 times 10 to the minus 4 is 1/2 mu n C ox. So did you say K or A? K is 5 times 10 to the minus 4. Then we multiply that by RS. And I get 0.25. Units of per volt. And I'll let you guys prove that if you care. Most of you probably won't use units, but I went through and made sure. That's how I made sure I didn't miss anything on the deal. All right. For B, I wound up getting 0.8 unitless. And for C, I wound up getting negative 1.246 volts. Using these values, I got VGS is equal to 1.146 volts or negative 4.346 volts. Two solutions because it's a quadratic equation, there has to be. Which one of these is correct? The positive one, 1.146. Why? So 4.3, it's negative 4.36. I would argue that the reason we have to choose the positive value is because if we chose the negative value, it's not greater than VTH, and so the device isn't on. So we have to choose the one that makes the device actually turn on, or because our assumption here in the saturation region is that at a minimum, it's on, right? Seeing that negative 4.346 is kind of outside the range of what we should expect for a voltage that we would assume would be between 1.8 volts and ground is okay, but it might not always work out that exactly neat, okay? We don't know what the voltage drop across our 500 ohm resistor is, so we really can't say what we're expecting that number to be, but only one of the two options is ever going to wind up with the transistor being on, so that's the one we need to go with. All right, so how can we further test whether we have made the right assumption for the device being in saturation? Well, now that we know VGS, we can calculate the corresponding drain current ID, right? So in this case, ID will be 1/2 mu n Cox W over L, or 5 times 10 to the minus 4, as Vitaly pointed out, times VGS minus VTH quantity squared, and that is equal to 278.576 microamps, which seems like a reasonable-ish number. But to determine whether or not the device is in saturation, we need to compare the quantity VGS TH to the quantity VDS, right? Because if VDS is larger than our overdrive voltage, it's in saturation. And when VDS is smaller than our overdrive voltage, we know that it's in triode, and so we have to effectively start from scratch and do something else. So VDS is simply VD minus VS. So that is going to reduce to VDD minus ID times RS plus RD. Maybe this one will be a little bit easier for you guys to compute. Go ahead and tell me what that number turns out to be. Based on the ID of 278.576 microamps. .686 volts, all right. And what's VGS minus VTH? 1.146 minus 0.4 is 0.746. So, was our assumption of this guy operating in the saturation region correct? We did 9 of these the other day. How can we tell? If VDS is greater than VGS minus VTH, it's saturated. If VDS is less than VGS minus VTH, it's triode. So this one is in the triode region of operation. Okay, so all the work that we've done to this point was useless. Now, here I'm going to show you guys the math involved with going through and figuring out our fundamental equations for triode operation. All right, we're going to come back to this guy in a second. So this is where I said we can tell that what VD, VG, and VS are very easily, much more so than we could determine what our terminal voltage were for a BJT circuit, but this is where it's significantly harder than a BJT circuit. All right, so so in the triode region, so let's start with what we have here, okay? Everything that we have done really is okay, except we're using the wrong equation for the current. Yes?
All this works for the P1 as well.
If you change, yep, everything, just change the subscripts and use VTHP. And everything that we're doing works. All this analysis should be. Yep. So in the triode region, we find that VGS is equal to VDD times R2 over R1 plus R2 minus mu n Cox W over L VGS minus VTH times VDS minus 1/2 VDS squared, all of this times RS. So here we have one equation with two unknowns, so we could take a guess at what we expect VGS to be or VDS to be, and then do an iterative process to figure out what the other one is. To do that, though, we'd really need a second equation, so I'll go ahead and write that guy down as well. VDS is equal to VDD minus mu n Cox W over L VGS minus VTH VDS minus 1/2 VDS squared times RD plus RS. Okay, so we have two equations and two unknowns. Because we have polynomial relationships, it usually takes significantly more than the 3 or 4 iterations that we were able to solve a BJT circuit with, because they have an exponential relationship between the current and voltage. This polynomial-based relationship means that we should expect 9 to 10 iterations, which to me sounds awful. So what I did at about 4 o'clock this morning is I made a MathCAD worksheet to solve for all the different possible permutations, okay? So that's the one for self-bias. We're not quite there yet. So Nmos full resistor bias worksheet where I just put in the values. The only thing that should look potentially weird to you guys is this capital gamma here. I set it as 300 nanometers because I am used to teaching a class on this stuff where we use a specific technology node on semiconductors C5 process, which has a scaling factor of 300 nanometers. So I'm just used to putting that in. So that's what I use here. Does not matter whatsoever. You could just not use units on the width and the length and you'd be fine. So we got the exact same values and all that kind of good stuff and saw that VDS was less than VGS1 minus VTH. So let me come down here to the bottom where I have my triode situation. Just simple 2 equations, 2 unknowns. One thing that you want to make sure to do if you go this route, which I would highly encourage you to do so, I chose a VGS value of 1 just arbitrarily, and you need to make sure that you choose VDS less than VGS, because you know that this guy is operating in the triode region where at a minimum, VDS needs to be less than VGS minus VTH. So I got these numbers, but if I were to do what I normally do, and just put everything with a guess value of 1. Well, it's not working right now. Of course it isn't. So if I chose a larger guess value for VDS, I can see that VDS is much larger than VDS is larger than VGS, which would be not operating in the triode region. So we have to pay attention to the fact that there are quadratic-based relationships that are going to have two solutions. We have to make sure our solution makes sense. So just as a rule of thumb, make VDS less than VGS minus VTH, and you're going to force it to pick the right one. Okay, so we can see here that we have a VDS of 690 millivolts, VGS minus VTH of 747 millivolts. So we are in triode conditions, and then our diode, our drain current comes out to be 207.408 microamps. Okay, so using MathCAD is a smart way to go here. All right. We still got 15 minutes, so I think I can finish this guy up. So let's circle back around to our original example problem and say then what value of RD would make this guy operate on the edge of saturation. So our new circuit, which is the same as our old circuit, except now we don't know what the value of RD is. Looks like this. Gate, drain, and source. And again, we're going to use VTH 0.4 volts and mu n Theox is 200 microamps per volt squared. And it doesn't really matter what lambda our common length, channel length modulation coefficient is, because we're at the edge of saturation, which means there shouldn't be any channel length modulation by definition. VDS is going to be exactly equal to VGS minus VTH. So with that in mind, well, I'll let you guys finish copying all this stuff up. Working on things. And we have a power supply voltage of 1.8 volts. All right, so with all this in mind, I'm going to go revisit the work we did initially. All right. So in our equations for VGS here, right, which we solved and all that kind of jazz, does the resistance RD show up once? No, not at all, not even a little bit. So that means that all the work we did there is still good for what we are about to do. So we know that VGS is going to have this value because that is what's happening when this guy is in saturation. And we can use that number to back calculate what value of RD makes that work. So with VGS equal to 1 oh gosh, where did I write it down? .146 volts and ID, our drain current, at 278.576 microamps based on our prior work. At the edge of saturation, VDS is equal to VGS minus VTH, which is 0.746 volts for our threshold voltage of 0.4 volts. We also know that VDS is equal to VDD minus ID RD minus ID RS. And so we can mathematically manipulate this guy and find that RD is simply VDD minus VGS minus VTH minus RS, all divided by ID, is equal to 3.282 kiloohms. So simple enough to figure out what value of a particular resistor does what. We can verify this in the MathCAD worksheet pretty easily, but we're running lowish on time. So any question about the assumptions and work we did there, where I guess really the only assumption was that the edge of saturation means exactly that VDS is equal to VGS minus VTH, right? Okay, so the last example that I want to work for today, because we're running out of time, is I want us to determine the operating point of this guy. Exact same circuit, except that now RD is a 2 kilo ohm resistor. Two, 1.8 volts here. Threshold voltage 0.4. UN C aux 200 microamps per volt squared. And I'm going to specify a value of lambda here, meaning we cannot ignore channel length modulation. And the reason why I'm taking channel length modulation into effect is because we have a drain resistance that is significantly under the threshold of what would cause this guy to be at the edge of saturation, meaning I would assume now it's fairly deep into the saturation region. And since it's deep into the saturation region, we should expect channel length modulation to play some role. So with channel length modulation present, or I'll give you guys a minute to finish copying that down. our fundamental equations become VGS is equal to VDD times R2 over R1 plus R2 minus 1/2 mu n Cox W over L, VGS minus VTH, quantity squared, 1 plus lambda, excuse me, getting ahead of myself, VDS multiplied by RS. So we have one equation with two unknown quantities, both VGS and VDS here. So we need another equation. VDS will be VDD minus one-half mu n Cox W over L, VGS minus VTH quantity squared times 1 plus lambda VDS, and all of this is multiplied by RD plus RS. Two equations, two unknowns, but again, we have pesky polynomials and all that kind of stuff, making everything difficult and making it take a long time to do the iterative process. So to this worksheet, I added a section for solving them with channel length modulation on. And if we go up to the very top, sorry, change this guy to 2 kilo ohms. Eventually. Everything else stays the same. With channel length modulation on, we can see that we get a VDS value of 1.052, which is larger than VGS minus VTH, so our assumption was correct. And then I solved for the drain current. So for your homeworks and all that kind of stuff, I would definitely create your own little MathCAD worksheet to make your life much, 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 much easier. If you do not currently have MathCAD, you are entitled to have it because you are a student of the College of Engineering and Science. If you go into the IESB and you head back towards IESB 112, the room where some of you maybe took Circuits 1 at this point. No, was the IESB wasn't open when you guys took Circuits. Okay, well, IESB 111 or 112 is the room where I usually teach Circuits 1. So I see this sign every day that I go over there to teach it. There's a sign on the wall on your way towards 112 for downloading SolidWorks and downloading MathCAD with a QR code and all that kind of jazz. So do that, or go talk to Miss Ashley Osborne down the hall, all the way down the hall in David Hall's big office thing, and she will get you hooked up with MathCAD. It will make your life much, much easier. I can tell you from looking at the homework problems, there are an awful lot of them where channel length modulation is not ignored, which means go spend the 10 minutes it takes to download MathCAD and install it and save yourself hours of homework suffering. On the exams, I will obviously have to allow you to neglect channel length modulation for you to solve these things without the use of a computer. Okay, so all right, so that's enough out of me for today. When we return next Friday, sweet Jesus, it was a week off. You guys don't do anything too terribly stupid for Mardi Gras. We'll talk about self-biased circuits, and then we'll get into MOSFET amplifiers, and we'll talk about MOSFET amplifiers until the quarter's over effectively. All right, you guys have a great rest of your day. If you have any questions, feel free to shoot me an email or come ask them now.